Thank you very much. Thank you very much for getting up. Thank you very much for the organizer for getting me here. It's my very, very first time in India, and I'm very excited about everything. Please be kind to me because everything I know about India, I know from 20-year-old Shah Rukh Khan movies. So yeah, we'll see how that goes. Anyway, my topic is an introduction to an overview of chromatic homotopy theory, which I think kind of fits because it has a lot of algebraic topology, but also it has a lot of patterns and relationships, dualities, open problems, and a lot of things happening there in research at the moment. But we probably won't see any chromatic homotopy theory today, but we have time. I wanted to start with a bit of a survey of stable model categories. I know, of course, that there is a prep talk on model categories, but I mean, I have to say the things that I need. And I mean, you can't hear about model categories often enough, so it will be okay, I think. So generally, a model category is a category with a notion of homotopy between the morphisms. So let me just write that. And that is not just a slogan or moral thing, it is quite a rigorous thing, which makes it so nice. So of course, you know what homotopy between continuous maps of good. Of course, you've heard of homotopy between continuous maps, which is a thing, but you will probably have also heard of chain homotopy of maps between chain complexes, and they're both called homotopy. And when you see those definitions for the first time, you think, yeah, of course, morally, they seem to be related in some way. But when you do model categories, you learn that they are not just morally somehow related, but they are actually both special cases of a very rigorous definition. If you think about model categories more from a categorical point of view, like yesterday you learned about localizations, localizations are trying to invert things, and you can also see model categories as a way of formally inverting some morphisms, because of course when you just say, oh, here is a map and I would like to make that an isomorphism by formally adding an inverse to the category, you don't know if that will work, if the result is still going to be a thing. And model categories are also a very beautiful and clean way of getting around many of these problems. So I'm not going to give you the full definition, just the bits that we actually need. So a model structure on a category C consists of the following data. And so you have distinguished classes of morphisms. If you're fancy, you can say subcategories, because they're all supposed to contain the identity and be closed under composition. So you have weak equivalences noted like so, fibrations and cofibrations, and they're supposed to satisfy some axioms, which I will just informally chat you through with a couple of exceptions. So these are the things that you would like to eventually formally invert. These will be the things that play the role of your homotopy equivalences. So if you are a topologist, think of those as maybe weak homotopy equivalences on spaces, or if you're more algebraically minded, you can think of homology isomorphisms on chain complexes. It's that sort of thing. And well, what are those mysterious axioms? So there's 5 of them. The first one is you're supposed to have all small limits and co-limits. If that's not a language you're used to, just ignore it. You're just supposed to have sums and products and push-outs and pullbacks and that sort of stuff. The second one is the 2 out of 3 axiom, which means that if you, it's for weak equivalences, so let me just write that down. So if you have an F and a G, and you can compose them, if 2 out of 3 of those are weak equivalences, then so is the third. And if you bear these examples in mind, then I would hope that that makes sense. Which order are there always? There's retracts, which you don't really need to know for my stuff, which just says the retracts of any of these things is one of those things again as well. There is lifting properties, which we also don't need today, at least not this morning. But I'd just like to point out that these lifting axioms are very similar to the things you would expect if you had heard these words before. So, because maybe you will have heard of fibrations and co-fibrations of topological spaces. And if you have, and when you see the full definition of model categories, you will see that those axioms are precisely supposed to model the behavior of fibrations and co-fibrations of topological spaces. And when you see the lifting axioms at some point, it's particularly evident in that, but it's quite a pain to write down. The only one that I will actually need today is the factorization axiom, which means that every morphism can be factored in 2 different ways. So many boards. So we can either factor it, so you can factor it in 2 ways, so that the first one is a co-fibration and the second one is a fibration. And in one case, this one would be weak equivalence, and the other one, the second one would be. And those are the axioms. And once you have those, you can do homotopy theory with it. So let's move there in a gentle way. Are you okay with reading the bottom row? Because it's too low or too small? Good. See, if you were my undergraduates, I'd say, if it's too small, solid row is free. Yeah, but it's difficult because it's so wide, isn't it? Okay, but do shout if you would like me to read anything out, or why it's bigger or smaller. Or... So, of course, this sort of thing lives off examples. There are actually lots of different ways of putting model structures on the same underlying category. This is why I deliberately wrote this down like this rather than saying a model category is. So already on topological spaces, there are several even standard ways of choosing these three things such that the axioms hold, but the most standard one is the following. You can make a model structure where the weak equivalences are exactly the weak homotopy equivalences. The cofibrations are retracts of relative CW complexes. So what is that? A relative CW complex is, let's do it the other way around, is a map like so, where this X comes from the var A by attaching cells to it. So you take an A and attach cells to it, get an X, and the inclusion of that into that would be a relative CW complex. And because of this axiom, you have to also throw in the retracts, but you don't have to care about that. And then the fibrations are basically how I met fibrations for the first time as an undergraduate. So they are all those maps such that if you put a CW complex here, and so you take one copy of A, and then you include it into the product of A with a unit interval, so the cylinder of A. So you can think of that as including A into the bottom of the cylinder on A. So for every commutative diagram like this, you have a lift here. And if this map satisfies that, then it's called a fibration. We learned that as the homotopy lifting property, because, yeah, it kind of means that if you have a homotopy downstairs, because you can think of such a map as a homotopy between what it does on the top of the cylinder and the bottom of the cylinder. And if you can lift the top of that homotopy, so the zero level or the bottom, depending on which way around your cylinder is, sorry. If you can lift one end of that homotopy, it means you can lift the entire homotopy. And that is also quite closely related to what that would look like. There are other model structures on topological spaces, depending on what you would like to do with it. But yeah, it's good to just have one. But to get more to the algebraic end of it, let's look at chain complexes in your favorite abelian category. If you, well, I mean, it could just be R modules or something like that, so don't worry about the whole generality of it. I'm even going to be a lot less general and say, just for ease of presentation, I would like just chain complexes concentrated in non-negative degrees. Well, actually, let's give this category a name. Let's just call it top. Things should have names, shouldn't they? So let's just say that we have an abelian category with enough projectives. If you think about R modules, or even more general, just think abelian groups if you want, then that is absolutely the case. Then you can make a model structure on here such that the weak equivalences are what I announced earlier. The homology isomorphisms, the fibrations are degree-wise surjections, and you only need that from n greater or equal to 1. And now, especially with that notation, it would be cute if the cofibrations would just be degree-wise injectives. Well, sorry. you need a little bit more for that. So you need degree-wise injections. I think that's where my printout cut off. I think it's actually n greater or equal to 0 with a projective co-kernel. And that is actually one of the first things that you can do when you really want to learn about model categories, is verify that this really satisfies those axioms. This is called the projective model structures for obvious reasons. You can also make an injective model structures if your abelian category has enough injectives. So just to mention that as an example of the fact that usually a category, you can put lots and lots of different model structures on it, depending what kind of things you would like to consider equivalent eventually. Like one of the reasons this formalism started out, for example, is that people didn't necessarily want to consider these morphisms to be the notion of equivalence for your spaces. People liked considering rational homotopy from the 60s onwards. So they would like to consider things equivalent such that homotopy groups tensored with Q would give you an isomorphism. And then you can't really talk about, homotopies with actual cylinders and stuff anymore. And one needs a more abstract formalism. And we get into how that works in a bit. But as I said, we need to do stable model categories. I'm completely lost, even worse than jet lag when it's not stable. So let's do more stable things. So the things that we will look at for chromatic homotopy theory is the category of spectra. Well, the category of spectra is a bit, it's not a good thing to say because there are lots and lots and lots of different types of spectra, not just lots of different model structures on a category, but there's also lots of different underlying categories because you need different technicalities to do certain things. Sadly, people found out the hard way in the late 20th century that you will never find a category of spectra that will do everything that you would like it to do. But thank goodness for our purposes, at least for my talks, we only need the easiest, simplest category of spectra that one can make. And then we're going to move to the stable homotopy category, which is the homotopy category of this. And stable homotopy theorists think that the homotopy category of this contains all of mathematics that is worth doing. And therefore, it is a very big and complicated category. And chromatic homotopy theory is going to be a way of studying this big and complicated category. So, the very simple category of spectra that I'd like to consider is the category of sequential spectra, which, so where the objects are sequences of pointed topological spaces so with base point together with structure maps from the suspension of one space, space number I, to the next one. And morphisms are going to be degree-wise maps of pointed topological spaces that commute with the respective structure maps in every degree. And I mean, as an example, I mean, the best spectrum is the sphere spectrum, which there's so many different spheres to write down. Let me do it bold. Probably drop the bold. Remind me if it gets confusing. So you can just put the n sphere for your respective n's in each position, and then the structure maps are the canonical isomorphisms identifying the suspension of the I-dimensional sphere with the I+1 dimensional sphere. So you could actually do this with any topological space and just put the space at the front and then just keep suspending and keep going, which is a nice way of saying that you can basically include all of unstable homotopy theory into what will be stable homotopy theory. Well, why would you do that? Well, no, it doesn't have any properties, just a map. Of course, the map is part of the data of the spectrum. So different maps give you a different spectrum. So here, I didn't write it down what the map is because I said what it is. But yeah, the object X depends on what those maps are. Because once you have a thing like that, you can define its homotopy groups. And how would you do that? Well, it is not very surprisingly made out of homotopy groups of what's inside of it. I always get the indices wrong. So you make the homotopy groups of such a thing out of the homotopy groups of what's inside. But how? What do I mean by that? Always have to check the indices. So you start, you write down the following sequence. While you have something like that, the n is always the difference between the position in the spectrum and whatever you put here. The first thing you do is you apply the suspension functor and you get to phi n plus k plus 1 of the suspension of xk, because suspension of that sphere gives you one more sphere, and then suspension of this is just suspension of this. And then you can apply the structure map and get to the next point in your spectrum and obtain a group with exactly the same difference between the index of the homotopy group and the index of the spectrum. And then you take the co-limit of that, which is not that particularly abstract, because Poincaré's suspension theorem tells you that if you put in a CW complex, then after a certain point, this sequence becomes stable. It means it just repeats, and the co-limit is just going to be what this sequence becomes eventually. So that is why I think stable homotopy theory is really, really lovely and clean, because you kind of cut away all the mess, all the frazzled bits at the beginning, and just look at the nice things it becomes eventually. So this becomes particularly interesting when you put in a sphere spectrum and you would like to look at stable homotopy groups of spheres, which are a lot of fun, aren't they? So yeah, and then I should say that you can make a model structure of these things by where the weak equivalences are the pi star isomorphisms again. You can make others, and we will, but that's the one to start with. So, that's normally in these axioms, the weak equivalences are really the star, aren't they? They are the reason one does that, because these are the things that tell you when two spaces are equivalent or not. And these are the things that will become your homotopy equivalences, the things you're going to formally invert. So these are really the things that you care about. And therefore, it is kind of okay to think that these are just technical supporting agents that you don't really need to talk about that much. And it is indeed true, but there are some very good practical things about them that I'd like to now briefly look at. By the way, I don't think you put the counter on a laptop, so it's not going to make a ring-a-ding. Yeah, you need, because it's a bit, yeah. I wanted to ring. But I get another chance, right? Should try and make it copy John's doorbell. Now, Neil is not here to ask him if that is sufficiently neat. He thinks it's clean. So, one thing that you've kind of already seen without seeing it in this context is, of course, in every category, there are objects which are particularly nice. And one can make this formal in this context. It's lower. We say that an object is cofibrant if the map from the initial object into it is a cofibration. And we say that X is fibrant. He's lisping on the board. It's fibrant if the map into the terminal object is a fibration. If you're not seeing initial objects or terminal objects, think of zero object or the point or something like that. And what is that really good for? Well, let's look at the examples which, thanks to the enormous width of the board, are still there, because normally whenever I give a talk like that, I will talk about things I've just erased. So if we're looking at the model structure here on topological spaces and ask ourselves, okay, so what is a cofibrant space? A cofibrant space would be something where you put a point here and say, okay, that is something which, where this space, like here you have a point, and here you have something where you've attached cell complexes to a point. So in this model structure, you get that CW complexes are cofibrant. That sounds nice, doesn't it? So if we look at that model structure of chain complexes over there, we can ask ourselves, so what is it like there? Because there the initial object and the terminal object are the zero object. So if you look at the definition of fibrations and co-fibrations, and you look at it for a few seconds and ask yourselves what happens if you put the zero object in the correct place. Well, I mean, if you put the zero object here, you're asking for something for the zero map to be degree-wise surjective, and that happens quite often, doesn't it? So in here, all chain complexes are fibrant. And now here, if you think about the zero object here, you're asking for the map from zero into something to be injective. Well, that's good, that happens. With projective co-kernel, well, if that is the zero object, then the co-kernel is just d degree-wise itself. So here you get that cofibrant is equivalent to degree-wise projective. But I mean, that's all very nice, but we all know that not all objects are naturally nice. But the good thing about model structures, and particularly this axiom, is we can always take every object and replace it with a nice object that's weakly equivalent to the original one. So I will not erase it yet. So you can therefore, you can form a cofibrant replacement by simply taking this map and throwing the factorization axiom on it. Well, you should do it the right way around. I've put the weak equivalence here, and you will obtain an object that is cofibrant, because this map will be a cofibration, and it is weakly equivalent to your original object. And likewise, you can do a fibrant replacement exactly the other way around by factoring this one into something which by definition is fibrant and weakly equivalent to your original thing. And if you look at these examples, what this means, well, it means in this case, you can take any topological space and you have a CW complex that maps into it with a pi-star isomorphism. And in the case of this kind of model structure, this gives you exactly the CW approximation that you would, for example, find in Hatcher's book. Here, I mean, fibrant replacement doesn't really give you anything here, but in the case of cofibrant replacement in this model structure, well, you have a chain complex, you replace it with something that is quasi-isomorphic to it, same homology groups, but it will be degree-wise projective. So what the cofibrant replacement in this model structure really is, it's a projective resolution. So in fact, yesterday, we've just seen lots of cofibrant replacement in Srikanth's talk. And maybe you didn't know it yet. And you can do the dual thing if you were doing the injective model structure I briefly mentioned, then this would exactly be the other way around. Everything would be cofibrant, and fibrant would be degree was injective, and a firing replacement would give you an injective resolution. So a lot of things that you will see in basic homological algebra, you can reinterpret as something in homotopy theory. And that is really what homotopy theorists like. They like to think that all math is just a special case of what they do. Whether or not that is a reasonable way of talking about it, you can discuss in the coffee break. Right. So, I mean, I've been saying homotopy, homotopy, homotopy. Let's actually say what that is. Neil is looking at me even when he's not here. Well, my selling point at the beginning was that you can do homotopy with these things. So homotopy without an actual physical cylinder that you can draw, but you can make cylinders without having to be able to draw them. So you start with defining what a cylinder object is. And in a way similar to yesterday morning, it's not just the object, but also the data of the maps that arise alongside it. So because of the limits and co-linkage axiom in a model category, you can form co-products. So either disjoint sum or, you know, and co-product, of course, comes with a fold map of the identities on both factors. And you can throw that into the factorization axiom, which I have just erased, and get a factorization like so. It's not a unique factorization, but that doesn't really matter. Whatever arises like that, we are allowed to call a cylinder object, because we can really think about it as you have two copies of X, you include it into something, and then you squash it. And this factorization is supposed to mimic exactly this picture. And now when you think about the picture that everybody draws when teaching topology about what homotopy is, where you draw a cylinder and say, oh, you have one map here and one map there, and then you can fill it in, you're pretending to do that with this particularly abstract object. So this is something called the left homotopy. So if you have two maps, let's say F and G, into something else, then you say that F and G are left homotopic if their co-products, so F here and G there, factors over a cylinder object. And then you can say that F and G are left homotopic. So that is really also one of the first selling points. You can do homotopy theory in model categories without having an actual unit interval, because of course in topological spaces, you can pick a cylinder by saying you just take space cross unit interval and you have a cylinder. But what would that be in rational homotopy theory or in some more algebraic things? Well, you don't need it. You can just do this. Once you have a model structure, you can do this. And well, sadly, I had to mention that it's a left homotopy. Whenever there's a left something, there's also right something normally. Yeah, let me just write it out because it's quicker than explaining to you why I'm not writing it out. There's also a notion of right homotopy. And for right homotopy, you use a path object where dually you factor the diagonal map into the product. And if you have spaces, well, then that can be the inclusion into the path space of X, so maps from the unit interval into X, and that map would be the respective evaluations at each end. And then you can say that F and G are right homotopic if they factor over path object. And that is exactly the dual way of defining what homotopy between maps is. But, well, that would give you right homotopy. And of course, we're not just left stable homotopy theorists or right stable homotopy theorists. We would like these things to be coherent in some way. And that is one of the reasons why I bothered to define these things over there. Because if your X and your Y are both fibrant and cofibrant, so if they are nice in both ways, then these notions become equivalent. So often with model categories, you have to replace things with something nicer. I mean, that's okay, you're allowed to. So then you get that left homotopic is equivalent to right homotopic. And you can just say, in this case, homotopic rather than left or right. And then also, being homotopic becomes an equivalence relation on a set of maps. And also, very, very nicely, and for me, when I saw that for the first time, that's really when all the definition stuff came together. A map is a weak equivalence if and only if it has a homotopy inverse in the classical sense that there is a morphism in the other direction such that the composites, the respective composites, are homotopic to the respective identities with that definition. And the beauty of this is you only need those axioms. So there are those 5 axioms, and the first one isn't really a very axiom where you have to do things. It's just you have limits and co-limits. It is not particularly deep or sophisticated. It is really just applying the axioms in the correct order. So the axioms are quite big. I mean, it's a long definition compared to other definitions you see in math. But once you have a definition and you have a model structure, you get things like that relatively quickly and easily. Well, but now we have this. We can finally start inverting these things and define a homotopy category. It's especially in what I do, I don't really work so much in the underlying model category context. I more or less work in the homotopy category of those things. And so, well, what is that? So if you have a model category C, then the homotopy category of C is the following things. So the objects of the homotopy category are just the same as the objects of your original underlying category. But for the morphisms, you take homotopy classes of morphisms rather than the morphisms you had. And because of that little subtlety over here, in order to be allowed to really do that, what you have to do is you have to take a cofibrant replacement of the first and then a fibrant replacement of the second. That is actually enough to get an equivalence relation. But if I wanted to write down all the properties at once, you might as well ask for both. And then you can take homotopy classes with respect to that equivalence relation. And, well, examples of these things. So you can, the derived category of your favorite abelian category is exactly the homotopy category of a model structure with H-star isomorphisms as weak equivalences. Just that the cofibrations are a bit harder to write down than what I did, but it's very, very similar. You can ignore the subtleties here, but that is the homotopy category of a model category. And one nice thing in there is that if you take, so by the way, the notation that I like to use for these things is square brackets. So in here, if you take just, let's say, A and B in A, and you take a chain complex that is just A concentrated in degree n and B concentrated in degree m, and you look at morphisms of that in the homotopy category, then this turns out to be an X group. And now I have to look at the indices. Oh, yes, I do. It's X n minus n. And that is something that you can also get from just writing down the definitions. Replace cofibrantly, replace fibrantly. You use right homotopies for this one, I think. Write down what is the path object, what does it mean for things to be related by a path object, and you come to the fact that that is just how to define X groups. So in fact, yesterday morning in both talks, whenever the speakers were writing on X groups, they were really doing homotopy theory. So if you've ever seen an X group, you can now think of them like that. I mean, of course, that is more of a curiosity. I don't think anybody gains anything about what you do by knowing that it's also something like that. But one of the reasons I really like topology, we were talking about our undergraduate topology lectures this morning, is seeing how seemingly different things come together in in a bigger context. Right. And well, really the most important one, for me at least, is going to be the stable homotopy category. Sometimes I just write SHC, which is homotopy category of spectra with respect to pi star isomorphisms. But of course, if you have categories with special structure, you also need morphisms that respect that structure. And those morphisms are the so-called Quillen adjunctions. So if you have two model categories, then you have to relate them with functors that respect what makes a model category, right? By the way, I will always write left adjoints on top. And you might think, okay, so something that respects the model structure surely is something that preserves all the three things, but that's far too much. So the correct definition is that the left adjoint should preserve cofibrations and acyclic cofibrations, which is equivalent, so you don't even have to ask for that separately, to asking for the right adjoint to preserve fibrations and acyclic fibrations. And when I say that's the correct definition, I mean, what do I mean by that? Who says that it's correct? Well, that is precisely what you need in order for those functors to give you a well-defined adjunction on the level of homotopy categories. So this induces you an adjunction on these guys, where this one is called the left derived functor of F, and the right derived functor of G. And that is why it's the correct definition, because that is really what you want. And a Quillen equivalence is going to be a Quillen adjunction that induces you an equivalence of the homotopy categories. Quillen equivalences, well, they are the holy grail of things that one would like to do, because Quillen equivalences do not just induce you an equivalence of model category, of homotopy categories. They induce you equivalences of many, many, many other structures that you can do with model structures that I haven't even talked about yet. So Quillen equivalent model categories have the same homotopy theory. And that is, for example, why it doesn't matter in some sense what category of spectra you would work with, because well, maybe that is your first encounter with spectra, but or there is lots more, but it has been proved that they're kind of all doing the same thing. So you can pick whatever technical category you like for your personal purposes and goals, because at the end of the day, whatever you pick, they're all going to be Quillen equivalent to each other, which is a very non-trivial result, but it's true. So now it's finally time to say what a stable model category is, because so far none of this has been, well, particularly stable. So from now on, all my model categories are going to be pointed. Abstractly, that means initial and terminal object degree. In practice, that's pointed. Algebraic things are pointed because they have a zero object. So for the algebraic side of things, pointed means having a zero object. For the topological side of things, just means things have a base point. And once you do that, you can define suspension and loop functors. So you take your map into a cylinder object of your choice, and you can take the push out over the trivial map, and that thing is going to be called the suspension of X. So if you've seen suspension of spaces, well, a suspension is a cylinder with the top and bottom closed, right? And so that is exactly that. You take a cylinder and that's the top and the bottom, and you close it in a more abstract way. And similarly, you can define a path object of a space dually by taking a map from a path object into the product. And then, what am I doing? You're taking a pullback over the zero object, and that is going to be loop object. If you think of loops as paths that have the same start and end point, that is exactly what this is mimicking. So that's the start and end point of your path, and that's the evaluation of start and end point, and saying that, well, they all have to have the same start and end point, namely your base point. That is precisely what this diagram is saying. And yeah, that defines you suspension and loop functors, not just something you can apply to objects, but functors. And then the theorem is that this is in fact an adjunction. Well, how can you see this? And that is really, really nice. I learned that when reading Quillen's article, and everyone says, oh, Quillen's article, that's so horrible to read, don't that? No, it's actually really, really nice. So I highly recommend it. So if you're thinking about it, if you look at what this is and what that is, especially because of this beautifully white blackboard, which this morning really plays into my timings unexpectedly well. Look at these things. So by definition, that is a map. That's maps from the cylinder object into Y, which are trivial on the top and the bottom of the cylinder. So in other words, this is homotopies. It's left homotopies from the zero map from X to Y to itself. And if you look at this, for the same reason, this is right homotopies from the zero map from X to Y to itself. And if you believe that there is a 1-1 correspondence between left and right homotopies, then you can believe that that's the same. However, this involves all kinds of choices, lots of choices, because that's not unique. That's not unique. You have to replace them coefficiently, infinitely, and everything. And it becomes a big mess. And because of all those choices, you only get an adjunction on the homotopy categories rather than C on the nose. And I know that that's a big mess because I wrote it down for my book. Lots of trees died for that proof. And yeah, then a model category is stable if that is an equivalence of categories. So if sigma and omega one of the PhD students in Warwick, where John is, she's got a tattoo of a sigma on her left hand and an omega on her right hand or wrist. And that's great. Anyway, so back to the examples, which are certainly not there anymore. So topological spaces, not stable. Yes, I mean, you can start with whatever your favorite homotopy groups of spheres are. Start with that one, that's trivial. Then you can apply suspension. And get that. And therefore, suspension is absolutely not an isomorphism here. So that is not will not give an equivalence of categories. But if you go to here, so now I look at the unbounded ones. Chain complexes is stable. And now I should have written that down. I did actually write that down. Oh, actually, chain complex is not a derived category. You can sit down again and work out what is the cylinder object, what is the path object, what does this all mean? And then just from the definition, you get that suspension and loop are just the respective degree shift functors. And of course, you can take a chain complex shifted that way, and that gives you an equivalence of categories. So that's a nice category. And spectra is stable because you can work out from the definition of homotopy groups that the unit of the adjunction is a pi-star isomorphism, because if you are in this co-limit world, then whether or not you apply some sigmas and omegas to it doesn't really matter anymore. So these ones are the good guys. But why are they good? Not just some moral things about neater homotopy groups. Well, that's all very nice, but I mean, come on, who cares? So one important theorem is that if C is stable, then the homotopy category of C is triangulated. So I am not actually assuming that everybody knows what that means, and you don't really have to, but just triangulated means that your category comes with so-called distinguished triangles that look like that with some properties. And once you have that, you can make very nice 2 out of 3 arguments, very similar to having exact sequences. You can apply homological and cohomological functors and get long exact sequences and do nice algebraic arguments. You can suddenly talk about what it means to be generated, like the whole cellularization thing that we saw means exactly that. You take an object and you take your triangles and your coproducts and you let it generate things. And for that, you need really the triangulated framework. So you're getting all this great structure just in the stable context. And yeah, I think I've got precisely 2 more minutes, haven't I? So 9 minutes. These clocks are not right, are they? Am I just picking the clock that's what I wanted to do? Well, then I can motivate things even better. Because now, finally, however many minutes before the end, I can actually tell you what the title of my talk means. I need a second. So in particular, of course, that means the stable homotopy category is triangulated, and it is a big, big, big important category. So in chromatic homotopy theory, we study the structure of the stable homotopy category using certain methods. And well, I've already told you that contains all of unstable homotopy theory, but just including it as spectra. It also contains all of algebra, because you can include all of algebra in some sense using Eilenberg-MacLane functors. So you know you can form an Eilenberg-MacLane spectrum, Eilenberg-MacLane space, which has certain homotopy groups. And you can similarly define an Eilenberg-MacLane spectra for groups, even for chain complex and differential graded algebra. So there are suitable Eilenberg-MacLane functors which include you all of interesting algebra in here. So there is a lot living in here. So it's very big and very complicated. So how does one study this big and complicated thing? By just looking at certain parts of it almost separately. So instead of inverting the pi star isomorphisms, we formally invert the E star isomorphisms for E, some kind of homology theory. So until next time, maybe I'd like you to think about what is your favorite homology theory. Maybe it's something to do with cobordism. Maybe it is just singular homology theory. Maybe it's K-theory. So rather than saying 2 things are the same if they have the same homotopy groups, you can also form a model structure by saying 2 things are the same if they have the same homology groups of your favorite homology theory. And for chromatic homotopy theory, we will be looking at certain homology theories, specially defined for a purpose, how they will decompose this into more manageable layers, how these layers interact with each other. And that all sounds awfully abstract, but we will start with some very simple algebraic examples and then work our way up to the other layers. So hopefully it will be relatively pain-free. And then maybe by the end of it, I will just get a little bit of time telling you what people do with this sort of thing now. But I mean, we don't really have to get there. Just the journey, I think, is very interesting because it passes so many different areas and results of topology. So hopefully, even though it sounds quite niche, there will be something for everyone in there. So thank you very much. That's it for the now.
Okay, are there any questions for the speaker?
Hello. So on the leftmost board, you mentioned that sigma and omega are only defined on the homotopy category.
Yeah.
We'd prefer to have those at the point set level, right? So does that change if you have functoriality of the factorizations?
Oh. I think you can probably, well, first of all, I'm not a big fan of functorial factorization, but even assuming that you have one, I think you might get on the nose functors, but for the adjunction, you definitely need the homotopy category.
Okay, yeah. Thank you.
Are there other questions?
You can always ask me at coffee or lunch, or if you don't want to do it here.
If there are no other questions, let's thank the speaker once more.